Welcome to this course on the foundations of continuum mechanics. Today we will continue our discussion on the velocity gradient tensor. We will talk what happens to this tensor under infinitesimal deformations, and this will be followed with a discussion on the rate of rotation, that is the Wij tensor. So let us get started. So we have defined the rate of deformation Dij, that was defined in the last lecture, which is the symmetric part of the velocity gradient tensor, and we have defined the strain tensor, which is epsilon ij, which was defined for an infinitesimal deformation case. So now we'll want to link these, or we want to figure out what is the relationship between these two quantities. Because we said that when we defined the velocity gradient tensor, there is no restriction on the deformations being small. So let us first work with finite deformations. So in finite deformation theory, the Lagrangian finite strain tensor, well, twice of that was defined as C minus I, where C is the Green's deformation tensor, and this is F transpose F minus I, where F is the deformation gradient tensor. So in the initial notation, I can write twice EAB is FIA times FIB minus delta AB. Now I take a material derivative of both sides. So this becomes twice EAB dot, and that is FIA derivative times FIB plus FIA times FIB dot. And the delta is gone because delta is a constant, so its time derivative is a 0. Now F dot was defined as L times F. So this is Lij times Fja, this quantity. And in the second term, we have Fia times Lij times Fjb, which is this quantity. Now again, I do some index manipulation. So this becomes Fja. So I swap the indices I and j in the second term. This becomes Lji, and this becomes Fib. And now you can see that the index of Fib is the same, and the index of Fja are also the same. So this becomes Fja times Fib times Lij plus Lji, and this is twice EAB dot. And we know that L plus L transpose is twice of D. That's the definition of the symmetric part of L. So this becomes, so let's write this as F transpose Aj times twice Dji. Now remember, D is symmetric, so it doesn't matter if I write Dij or Dji, and then we have an Fib. So this becomes, in the symbolic notation, this is twice of E dot is F transpose dot D dot F. And this I'll call A for today because I'll need this for further discussion. Now let's recall what was displacement. So Ui was defined as xi minus capital Xi. So if I take a derivative with respect to capital Xa, this is what we get. So we can write xi comma a, which basically is Fia, as ui comma a plus delta Ia. Now we apply the condition for small deformations. The different terms of the displacement gradient tensor, that is this tensor, are small. So when I say small, that means they are much smaller than 1. So if I add an identity to it, it's like I'm adding a 1 to it. So I can write my Fia approximately as delta Ia, because ui comma a have terms which are much smaller than 1. So in symbolic notation, this means that f is approximately identity for small deformations. So if we substitute this in a, what we get is twice of E dot is an I dot 2D dot ni, which simply is twice of D. So this gives us E dot is D. But we also know that under small deformations, our E becomes an epsilon. So we can write epsilon dot is a D. And that's a very interesting result. What we have shown is that the rate of deformation tensor is the time rate change of our strain tensor epsilon. Having shown this interesting result, now we move on to the second part of today's lecture, that is on rate of rotation. In the last lecture, we had shown that dx dot upon dx or lambda dot upon lambda was equal to ndn. So in this expression, if I use d equal to 0, this implies that my dx dot is going to be 0. So the meaning of that is that elements do not change length. Additionally, we also showed that the rate of decrease of the angle theta between two perpendicular vectors n1 hat and n2 hat is n1 dot d, or twice of d dot n2. So in this case, if d is 0, then this implies that theta dot is a 0. So what does that mean? That means the angle between any two perpendicular vectors does not change. So what we notice is that if our rate of deformation tensor d is 0, there's no change in the length of elements and there is no change in the angle between any two perpendicular vectors. So that corresponds to a rigid body rotation. So let's go back to the equation that we had written last time, that is n hat dot plus n hat times lambda dot upon lambda was L dotted with an n hat. So you can go to the last lecture and have a look at this equation. So in the symbolic notation, I write this as ni dot plus ni, and this lambda dot upon lambda was shown to be dkq times nk nq, and this is lij nj. So I can write my ni dot, that's a time rate change of the vector n, as, and further we can write L as dijnj plus wij, there's an nj. So this I'll write as wijnj first, and then I'll keep the terms which have a d in it. So this is dijnj minus ni times nk and so on. And we will box this as we'll need this now. So again, if our d is 0, what that means is that ni dot becomes simply wij nj. Now that we have the algebra in place, let us try to interpret what's happening here. So we are interpreting the situation where d is 0 because we want to analyze pure rotation cases. So we have a dx vector which is denoted by this n hat direction. And n hat dot, which is this quantity, is the rate of change of n hat. But remember, we said and we showed earlier, both mathematically and conceptually, that n hat can only rotate. It cannot change its length by definition of a unit vector. So n hat dot is the rate of rotation of n hat. Now in this case, as we showed, when d is 0, it's a pure rotation case anyways. So the whole d small x vector rotates. And the information about this rate of rotation is coming purely from this w. So I can conclude that since in this case we have a rigid body rotation and the rate of rotation of the vector is given as wi, j and j. So w contains the information for the rigid body rotation. And this is the reason it's called a spin or a vorticity tensor, because it creates a spin in the material. Now this was for the case when d is 0. So I'll summarize because it can very quickly get confusing, that if my d is 0, this implies it's a rigid body rotation, and my n hat dot is given as w times n hat. So w contains the information about rigid body rotation. Well, in this case, it's a rate of rotation because we're talking about n hat dot. So this is in fluid mechanics mostly that W is used. So W is about things rotating continuously. So I have learned that W contains information about rigid body rotation. So let's underline that because that's important. Now let's take a case where D is not 0 and then see what happens. So for D not equal to 0, we consider the elements, that is the elements n hat, along the principal directions of D. Now this is our choice. We are analyzing what happens to vectors which are oriented along the principal directions of the rate of deformation tensor D. So that means my n hats are written as n hat P, where P is 1, 2 or 3, which represent the principal directions of D. So we go back to our equation number B here and use this. So equation B gave us n dot I, but this time we are doing it for one of the principal directions of D. So I write a bracket P as a superscript, and this is equal to Wij times Njp plus Dij Njp minus Nip times Nk dkq nq. Now this term, by the definition of principal directions, becomes the pth principal value times Nip, and similarly this term becomes the pth principal value times Nk. But we already have an Npk here, so this dotted with this will become a 1. So I write my n dot ip as wij npj plus dp times nip minus nip times dp. So we can see that these terms cancel out. And that's very interesting because in the symbolic notation, we get the rate of rotation of any principal direction of D as W times n hat P. But W contained information about rigid body rotation. By that argument, what we conclude is that the principal directions of D are undergoing a rigid body rotation. Now that is a very interesting idea because we notice that the principal directions of D are special. They undergo a pure rigid body rotation. But the question that appears in our mind is that when D was 0, the elements were not stretching, they were purely rotating. But here what we have found out is the rate of rotation for the unit vector. The unit vector only rotates. It cannot do any other thing. But if you take the element dx, which is along the principal direction of the rate of deformation tensor, is this elongating? Well, the answer is yes, because we have defined lambda dot upon lambda as n times d times n. So if you're talking about the principal directions, then this thing becomes dp. So the principal values of d tell us the rate of stretch of this element dx. So what's happening is that along the principal directions of d, these elements are stretching as well as rotating. And particularly this rotation is a rigid body rotation. Now, I'm sure I've confused you a lot here because I am saying that this rotation is a rigid body rotation. Now, the element is stretching and rotating. But can a rotation be a non-rigid body rotation? And the answer is yes. Let's have a look. So let's write the equation B again. So let us see these terms. Now dij and j is actually a vector. And you may remember from our discussion on the background mathematics, a vector can be written as its component along a given normal. So I write a component along n hat. Well, let's use the symbolic notation. So I call this d dot n. And then you have a component which is perpendicular to n hat. So this is along n hat. So we can always break a vector into a vector along a given vector and a vector which is perpendicular to that n hat. And what is this thing? This is the component of this vector d dot n. So this is our vector. So this is easy to see. So what we notice is that d n hat minus n dot d dot n times n hat is a vector which is perpendicular to n hat. Now this quantity is the same as this quantity. Now we definitely know that this dot of an n hat has to be perpendicular to it, because by definition n dot cannot be in the direction of n. So both these quantities have to be perpendicular to n, and we can easily see that this is perpendicular to n and this is also perpendicular to n. You can simply take a dot with n for both vectors and you will see it will be a 0. But this wij and j was because of rigid body rotation. That is, this wij and j was resulting in the n vector to rotate because of a rigid body rotation in the continuum. So what is this quantity? This quantity actually is called a stretch-induced rotation. So as I said, rotation can also be because of something other than a rigid body rotation. So when d is 0 or you are working along the principal directions of d, then the stretch induced rotation is a 0. But for all other general cases, we do have a component from the stretch induced rotation. To better understand an intuition for this stretch induced rotation, what I'll do is I'll give you two examples. And the two examples will be for cases where there is no W, that is, there is no pure rotation. And I will show you that vector elements are rotating. So that will give us an understanding that even without rigid body rotation, the rotation can happen. And that rotation as an inference is purely because of D, that is stretch-induced rotation. So in this first example, so let us say our velocity field is given in 2 dimensions as this vector. So from this, we calculate our L tensor, which is Vi comma j. So in 2 dimensions, it becomes del V1 by del X1, that is an A, then del V1 by del X2, that is a 0, and then del V2 by del X1, that's a 0, and then a del V2 by del X2, that's a minus B. And in this case, A and B are both positive quantities. So from this, we can get our rate of deformation tensor as the same tensor here, because D is the symmetric part of L, but L by itself is symmetric, and we get W as a 0. So W being 0 means that there is no rigid body rotation. So if there's no rigid body rotation, then all we can have is D. So let us look at an element which was made up from this dx1 and dx2 vectors. So now if we take this point A, which has coordinates L comma 0, if I look at the velocity field, I see that the velocity for this point A is along even hat direction, because x2 is 0 for this point A, and that is A times L. So this point A will tend to move to the right like this and reach a point, let's say this point A prime. Similarly, if I look at point B here, I should use the small symbols because we are working in the spatial coordinates. So this point B has a velocity which is negative because B is a positive number. So the velocity of this is downwards. Let's write the coordinates of B. So B is 0 comma L. And then the point B reaches a point here. So the element after some time stretches into something like this. Now what's happened to point Q? Well, point Q has gone here. So this vector, which was PQ, has now become this vector PQ prime. So we can clearly see that there is a rotation of this vector PQ to a vector PQ prime. And this rotation is because of D, because W was a 0. So different stretches in different directions results in a rotation. So I'm sure I've given you some intuitive feel of rotation happening because of different stretches. So this is a stretch-induced rotation. Let me give you another example. In this case, the velocity field is given as this. So from this, I can find L tensor as del V1 by del X1, that's a 0, del V1 by del X2, that's a C, then we have a del V2 by del X1, that's a C, and del V2 by del X2, that's a 0. Now this L is again a symmetric tensor. Although it's not diagonal this time, it is completely off diagonal, but from this we conclude that D is 0C C0 and W is again a 0. So if W is 0, that means there is no rigid body rotation. So let's see what happens to the elements geometrically. So again we start with our square. with points. So let us look at the velocity of the different points. So for point small a, we notice that its velocity, if I use this velocity field here, if I put x1 equal to L, I see the velocity is in purely the x2 direction, that is c times L. So this point A moves up and let's say reaches this point A prime. Similarly, if I look at point B from this expression again, then its velocity is purely in the x1 direction. So this point moves to the right. It reaches a point here. Let's call this B prime. So the velocity of point P is like this, and it goes to a point P prime here. So now let's look at the deformed element. And again, we can see that some rotation has resulted because of this D, because W was a 0. So from these two examples, we notice that W equal to 0 can also have rotation of elements which is due to D, and that is called the stretch induced rotation. So what happens is an element starts to rotate and it keeps rotating until it experiences a direction which is the eigen direction of D. But as soon as the vector reaches the eigen direction of D, then there is no rotation because of the stretch induced rotation as we noticed. And since W was a 0 for the previous two cases, that means the vector will stop rotating. So the flow field becomes very interesting. What you have to do is you have to find the eigen direction. Let's say the eigen direction is along this, which was the case for the second example here, as you can find out easily by taking eigen directions of this D tensor. So this eigen direction, which is at 45 degrees to our horizontal axis, so the flow field in this case will look something like this, which basically means is that vectors will be oriented so that all the fluid particles will eventually want to move parallel to the eigen directions of D. And this we're talking about a case where W is 0. So things will want to align with the eigen directions of D. So this is the qualitative nature of flow. Now again, this is something that you typically learn in an advanced fluid mechanics course where these ideas of continuum mechanics are linked to different fluid flow situations. But I want to give you a feel because the topic on kinematics can sometimes get quite confusing. Hopefully this will help you understand those situations. Elements rotate due to the stretch induced rotation and eventually they will align with the eigen directions or principal directions of D, because then there will be no more stretch induced rotation. Now one more thing which we noticed was, let us go back to the examples and have a look. Now for the first example, our D was diagonal, that is it did not have any off diagonal terms, so elements were purely stretching. And for the second example, our D was purely off diagonal, so elements were purely shearing. But both of these cases resulted in a rotation which was because of D, not because of W. And again, that's a very interesting idea that both these D's, that is this or this, they both are similar in nature. Because mathematically speaking, if you have a symmetric tensor like this, you can always bring it to a diagonal tensor by rotating your coordinate axes along the principal directions. So basically what that means is it was purely a choice of our axes that resulted in this nature of D. If I had chosen a different axis, I would have got different representation of D. So every symmetric tensor can be diagonalized. So that means both these tensors have a similar nature. So if I was looking along the principal coordinate axis of D, I would see a D looking like this. So then I would notice that it is because of the stretch of the different coordinate axes that results in a rotation of the vector PQ. And here I concluded that it was because of the shearing, that is the off-diagonal terms, that there was a rotation. But since both of these are purely because of our choice of the coordinate system, both of these are in a sense the same thing. So whether I call it a stretch-induced rotation or I call it a shear-induced rotation, it is the same thing. And this is exactly the reason that we call symmetric tensors in deformation as stretch tensors. So moving on, we will now talk about rotation vector. So since we have a skew symmetric W, we can define a dual vector associated with that, as we had discussed earlier in the course. So I'll write this as Wi as epsilon ijk, capital Wkj, where this is the dual vector of capital W. In fact, I can also define an inverse, just as I had shown earlier, that Wij can be obtained from a Wk vector. And remember, this is possible because a skew symmetric tensor has only 3 distinct components. So intuitively, we can define a dual vector associated with that. So for our case, this W vector can be written as this, plus I add another quantity to it, which is epsilon ijk times dkj. But see, this quantity is a 0 because d is symmetric and epsilon is skew symmetric. So this means this is a 0. So I can add a 0 to a quantity. There's no problem with that. And this results in, there's a W plus D, which is the velocity gradient tensor L. So I'll just write L here. And what was L? L was P, K, comma J. And this quantity here is simply half times the curl of the velocity vector field. So if you now look at the two-dimensional velocity field, what you will notice is that omega vector will be perpendicular to the plane of motion in 2D velocity field. Again, this is very analogous to what we had discussed earlier for 2D displacements when we had shown the rotation vector omega tilde as half times the curl of the displacement field. Now remember, this omega actually is the rate of rotation. So it's like an angular velocity. It's not an angle, it's a rate of change of angle. That's an angular velocity. So now that we understand that there is a dual vector, that's an angular velocity vector that is associated with the velocity field, let us do some analysis for the situation where our d is identically 0. That is, the rotation is purely because of W. So I can write this as dij plus wij times dxj. And if our d is identically 0 everywhere, I get my dvi, that's a relative velocity, as purely because of rigid body rotation. But now, since I know the relationship between this skew symmetric spin tensor and our angular velocity vector, I will substitute that here. So this becomes minus epsilon ijk wk dxj. And from here, you can easily see that this is the cross product of omega with dx. So for the situation where d is 0, that is for purely rigid body rotation, we see, let's think in terms of 2D. If you have a vector d small x, then the vector dv is perpendicular to dx, and that means this is purely rigid body rotation situation. So if I had a very light stick which was stretchable, let's think of a rubber stick, and I kept it in the flow like this stick will not stretch because my d is 0. So that means there is no stretching happening, it's a pure rotation, and this stick will start rotating counterclockwise in this case with an angular velocity of omega magnitude. So this brings us to the end of this lecture on velocity gradients and their interpretation, and this also brings us to the end of this module on kinematics. I hope you have been able to understand motion and how to describe motion in continuum mechanics. And with this, we have achieved one of the major learning outcomes of this course, which was to be able to quantify deformations using different quantities in continuum mechanics. So we learned about different types of tensors which help us quantify deformation in continuum mechanics. So now we are ready to be able to use all these quantities and develop balance laws. So this lecture will follow a tutorial where we will practice problems based on the topics we have discussed in this week. So thank you very much, and I will see you in the tutorial.